Have you ever noticed that almost every airplane, from small trainers to massive airliners, has one thing in common: a long, smooth, pointed nose? But have you ever wondered why? Because if airplanes are powered by engines, producing tens of thousands of pounds of thrust and weighing hundreds of tons, why would engineers care so much about the shape of just the front few feet? And here's something even stranger. A tiny change in the nose shape can dramatically increase fuel consumption, reduce speed, and even affect stability during flight. So why are airplane nose cones so pointed? And what exactly is happening to the air before it even reaches the wings? By the end of this video, you'll understand why this simple-looking shape is actually one of the most important aerodynamic designs ever created. Welcome back to Airspace Academy, where we uncover the engineering secrets hidden inside the flying machines we see every day. Let's dive in. Imagine you're flying at 850 kilometers per hour. At that speed, an aircraft isn't gently moving through the air. It's continuously crashing into billions upon billions of air molecules every second. A modern airliner weighs over 70 tons and slices through the atmosphere at nearly the speed of sound. Now imagine pushing your hand through water. You immediately feel resistance. The faster you push, the harder the water pushes back. Air behaves the same way. And for an airplane, that resistance is called drag. The challenge facing engineers is simple. How do you move a gigantic machine through the air while creating the least possible resistance? The answer begins at the very front of the aircraft: the nose. But here's where it gets interesting. The first airplanes weren't designed using advanced computers or wind tunnels. In the early days of aviation, engineers experimented constantly. Some aircraft had blunt noses, some had boxy fronts, some looked almost like flying carriages. And they quickly discovered something surprising. Aircraft with smoother, more streamlined noses flew faster and consumed less power. The reason wasn't obvious at first. But over time, aerodynamic research revealed a hidden battle taking place between the airplane and the air itself. And that discovery completely changed aircraft design. So let's simplify the idea. Think of air as a crowd of people standing in a hallway. Now imagine running straight into that crowd. Everyone gets pushed aside suddenly. Lots of chaos, lots of resistance. Now imagine someone walking through the crowd slowly while gently creating space ahead of them. Much smoother, much less effort. That's essentially what a pointed nose does. Instead of smashing directly into the air, it gradually guides the airflow around the aircraft. The air gets time to move aside smoothly. Less turbulence, less resistance, less drag. But that's not the full story. There are actually several aerodynamic jobs the nose cone performs simultaneously. First, it reduces pressure drag. When air hits a blunt surface, pressure builds up rapidly. That pressure acts like an invisible wall, pushing against the aircraft. A pointed nose spreads that pressure change over a longer distance. The result is a smoother airflow path. Second, it helps prevent flow separation. Imagine water flowing around a rock. Behind the rock, swirling eddies form. Air behaves similarly. If airflow separates from the aircraft surface, turbulent wake forms behind it. That turbulence creates enormous drag. A properly shaped nose helps keep the airflow attached to the aircraft for longer. Third, it prepares the airflow for everything behind it. The cockpit, the fuselage, the wings, the engines. All of them perform better when clean airflow reaches them. The nose is essentially setting the stage for the entire aircraft. Now let's see what actually happens during flight. Imagine a jet moving through the sky. The very first part touching untouched air is the nose cone. As the aircraft advances, air molecules begin compressing slightly ahead of the nose. Instead of encountering a flat wall, The air meets a smooth, curved surface. The airflow gradually divides. Some travels over the top. Some moves underneath. Some flows along the sides. Because the shape changes gradually, the air stays organized. Think of it like a highway splitting into multiple lanes instead of forcing all vehicles into a sudden sharp turn. The smoother the transition, the less energy gets wasted. And less wasted energy means lower drag, lower fuel burn, greater range, higher efficiency. This is the part nobody talks about. The perfect nose shape actually depends on speed. Aircraft flying at different speeds face different aerodynamic challenges. A small training aircraft flying at 200 kilometers per hour doesn't need the same nose shape as a fighter jet approaching the speed of sound. As aircraft get faster, airflow starts behaving in strange ways. Compression effects become important. Pressure waves begin forming, and eventually shock waves appear. That's why supersonic aircraft often have much sharper and longer noses than ordinary airliners. Engineers aren't just shaping metal. They're controlling how shock waves develop around the aircraft. And a small change can make a huge difference. Let's look at a real-world example. A commercial airliner spends thousands of hours flying every year. Even a tiny reduction in drag can save enormous amounts of fuel. Over the lifetime of a fleet, that can translate into millions of dollars in savings. That's why manufacturers spend countless hours testing nose shapes in wind tunnels and computer simulations. They aren't chasing a prettier design. They're chasing efficiency. And here's another fascinating detail. Most people think the nose cone exists only for aerodynamics, but it also houses critical equipment. Inside many airliner nose cones sits the weather radar system. That radar constantly scans ahead for storms, turbulence, and dangerous weather. So the nose cone isn't just cutting through the air. It's also helping pilots see what's coming long before they reach it. But here's something even more surprising. The nose cone itself is often made from special composite materials instead of metal. Why? Because radar signals need to pass through it. Metal would block those signals, so engineers had to create a structure that's aerodynamically efficient, strong enough to withstand flight loads, and transparent to radar waves at the same time. One component, multiple engineering challenges. And one final detail most people never notice. If you look carefully, airplane nose cones aren't actually perfectly pointed. They're rounded. That's because an infinitely sharp nose would create manufacturing problems, structural issues, and other aerodynamic penalties at subsonic speeds. Engineers discovered that a carefully rounded shape often performs better than an extremely sharp point. It's a perfect example of engineering optimization. Not the sharpest shape, not the strongest shape, not the cheapest shape, but the best overall compromise. So the next time you see an aircraft on the runway, take a look at the nose. What seems like a simple pointed front is actually a masterpiece of aerodynamic engineering. It's reducing drag, managing pressure, guiding airflow, protecting radar systems, improving fuel efficiency, and helping the entire aircraft perform better. Once you understand what's happening, the design suddenly feels obvious. Of course, the airplane needs a carefully shaped nose, because before the wings create lift, before the engines produce thrust, before anything else happens, the airplane must first convince the air to move out of the way. And that job begins at the nose. The world of flying machines is full of secrets. And in the next episode, we're revealing another one. Subscribe to Airspace Academy, and I'll see you in the next one.